Hello, we are going to be working on Edgenuity Precalculus, Section 6.6, called Solving Matrix Equations. There are two objectives to this section. One of them is to solve matrix equations using operations with matrices, and the other is to solve matrix equations by taking the inverse of a matrix. So these are the things that I will be going over today. Let's talk about solving something fairly simple. This is equivalent to a one-step equation. So essentially what we've got is matrix X plus matrix A equals matrix B. So X, A, and B. And I've written the X, A, and B under the matrices that they go with. So this one, as you can see, the X, as you can see, is the variable one, is the one that we want to know because that's the one that we don't have any numbers in the matrix for. So in order to do that, we just need X by itself the same way we would any other time. And so it's the same as traditional one-step equations. We subtract A on both sides, and we figure it out from there. So I'm going to erase what I just wrote and do it up with the other part there. So I want to do minus A, and I'll write it that way up there. And then down here, I'll do minus A, and I'll actually write the matrix. Okay? And so now I've got A over here, right? So one of the things that I'm going to do, if you've seen classes with me before, if you've had classes with me before, you know that I like to do plus negative instead of minus, like this, plus negative. And what that would do in this case is I would have to distribute that negative, treat it like a scalar -1 to multiply to both things, okay? So what that's going to do is for my next step, I'm going to have the X matrix, X1, X2, equals, because now I've subtracted that away, so it's not there anymore. It's a zero matrix, so I can ignore it, because any matrix times a zero matrix of that same size is that matrix. Same as we have it with real numbers, even complex numbers. Okay? And then I have to figure out this 8, 15, that matrix B, minus or plus the opposite of matrix A, which if I distribute that negative would give me +2, -5. I hope it's clear how I got that by distributing this negative to both of those things. Okay? And then I just need to figure out answers here. And you do elements with their matching elements. Okay? So 8 plus 2 is 10, and then 15 plus -5 is 10. It's a coincidence that they happen to both be 10 and doesn't mean anything. So what that implies is that x1 equals 10 and x2 equals 10. And so there we have our answer. I'll pause for a moment if there are questions. Give you a chance to ask questions. Give you a chance to look at it. Okay. So there being no questions, I will move on. So now let's look at, what if we had multiplication thrown into this, matrix multiplication thrown into this. So we've got a situation where we're doing a times x plus b equals c. So we know how to deal with the plus b, okay? Again, we're trying to get the x by itself. You can see that we've got a matrix X with all variables, so we're trying to get that matrix X by itself. Same thing will happen here. We'll do minus B and minus B. So what that'll give me is this AX, so 3, 2, 5, 5, times matrix X, X1, X2, equals, and then I just need to subtract these. So I'll subtract B, which will subtract matrix B over here, 1, 2. And then let me turn it into plus negative and distribute that negative inside, so like that. And so I get an answer of 2 plus negative 1 is 1, and negative 3 plus negative 2 is negative 5. And then I have to deal with this multiplication one, and this is where things get different, okay? So now I've got, let's call this matrix D. So I've got A times X equals D. Okay, A times X equals D. So in regular multiplication, you would divide by A on both sides, and that would get you X by itself. But you would only divide by A as a symbol of really multiplying by the reciprocal of A, that is the multiplicative inverse of A. And that's exactly what we're going to do here, but remember that matrix multiplication is not commutative. You can't do it in whatever order that you want. So it actually becomes very important what the order is. And it turns out that you always have to do the A inverse on the left. Okay? So like this. And then these two, A inverse times A, will give you the identity matrix. And the identity matrix times X is X. Because the identity matrix times any matrix that can be multiplied by it is that matrix, equals A inverse times D. So then we have to figure out A inverse and do that multiplication, okay? So what is A inverse? A inverse is 1 over the determinant of A times a new matrix, which we get by using A, and we take this diagonal and exchange the numbers. That's an awful looking 5. So 5 goes there, 3 goes there, and then we take this diagonal and we simply make each number the opposite sign, but we keep them there. So now I got to know the determinant of A. So let's see, the determinant of A, let me do some side work right here. The determinant of A is, let's see, we do 3 times 5, so it's 15, minus 2 times 5 is 10, so the determinant is 5, because you do these two multiplied minus these two multiplied. That's how we get the determinant. So then we've got that this is 1 over 5 times 5, negative 2, negative 5, 3, which is, well, 1/5 times 5 is 1. 1/5 times negative 2 is negative 2/5. 1/5 times negative 5 is negative 1, and 1/5 times 3 is 3/5. So there's the inverse. And now I just have to do A inverse times D. So that is this 1, negative 2/5, negative 1, and 3/5 times 1, negative 5. So just as a reminder, the only reason I can do this is because this is a 2 by 2 times a 2 by 1, and so the insides match, and I will get a 2 by 1 as my answer. So let's actually do the multiplication. That's first row to make the new first row, and it's first one times first one, second one times second one, and add them together, right? So it's first row times first column for matching elements, that is the first row, first column element times the first row, first column element plus the first row, second column element times the first column, second row, first column element. Try and keep everything together. So it's all this times all this with matching parts and then added together. So it's 1 times 1, which is 1, plus negative 2/5 times negative 5, which a negative times a negative is positive, and then you'd have 2 times 5 over 5. The 5s would cancel, so I would just get 2. And then that would be my first row. And then second row, it's the same thing. Second row times the column. Matching elements, add them together. So negative 1 times 1 is negative 1, plus 3/5 times negative 5, positive times a negative is a negative, and 3 times 5 over 5, 5 over 5 is 1, so 3 times 1 is 3, so we get negative 3, and so I get my matrix, this equals matrix X, remember, and so I get my matrix of 3 and negative 4 would equal matrix X. And so there is our answer. X1 would be 3, X2 would be negative 4. A lot involved in that. I'll pause for any questions. Okay, there being no questions, I will move on. Well, let's talk about using technology, Again, it will give you a matrix calculator in Edgenuity, but you can also use meta-calculator.com for this. And this works the exact same way. I've got A times X equals, let's call it B this time. And to solve it, I need to do A inverse times A times X equals A inverse times B, which is going to mean that matrix X is going to equal A inverse times B. And if you, let's actually look, I'm going to put this into MetaCalculator and let you see what I get. So I go to meta-calculator.com and I choose the matrix calculator. I hit Start Calculator, and matrix A is a 3 by 3, which is the default in MetaCalculator. And I start putting in my numbers. 3, 2, 5, 4, 2, 1, 2, 1, 1. And then matrix B is 3 rows, but it's only 1 column, so I need to change that description to 3 rows, 1 column. And then I need to put it in 3, 6, 5. And you will see that there are operations available to you, and one of those operations is A inverse times B, which is really nice. So you can just hit that button and it spits out an answer for you. So A inverse times B equals the 3 by 1 matrix, 19, negative 37, and 4. So I used metacalculator.com, meta-calculator.com to use technology to help me get that answer. All right? And that tells me what x1, x2, and x3 are. I just match up the elements. Okay, I will pause for questions. Let you get a look at that. I know there's not a lot to see on the board itself because we have technology doing it. Figuring out the inverse of a 3 by 3 matrix is pretty ugly, so we're going to let the technology do it for us. Computers are really good at working in matrices. In fact, the whole reason that we study matrices is because that's really how computers work. Okay? All right, well, there being no questions, let's move on. So one of the applications, one of the big major applications for matrices, and really the one that computers use it for quite often, is to solve systems of equations. So here is a system of equations, and what we have to do is turn this into a matrix. Okay, and here's the way that you do that. Matrix A is the coefficients from each term in the longer part of the expression. So you have to have all your variable terms on one side, all your constants on the other, because you're going to use all your variable terms, you're going to use their coefficients, that is the numbers attached to them, for matrix A. So this will be, it's 1x1, so that'll be 1, 2x2, so 2 will go right there, 3x1 will go right there, and 4x2, so the 4 will go right there, and there's my matrix A. Now, you need everything lined up correctly in order to be able to just kind of transfer this visually, right? And it doesn't really matter if you're using x1 and x2 or some other thing. We could have just as easily written this as a more traditional looking system, x plus 2y equals 11, and then 3x plus 4y equals 25. We don't, it's pretty common to use the x1 and x2 and x3 and x4 notation with matrices, mostly because we wind up doing extremely large matrices when we're doing this like for real life plugging things into computers. You don't just have a very small number of them, so it's not convenient to try and use different letters. You just use the same letter and you count up as much as possible. So that's why we're seeing the x1 and x2, because that's an anticipation of you understanding that we'd have an x3 and x4 and x5 and x6 and x7 and so on. So A times matrix X, and matrix X in this case will be X1, X2, or it might be X and Y, that sort of thing. And so there is our matrix X, and it equals matrix B, which is our constants, 11, 25, and there's our matrix B. So now we've got our AX equals B. We're going to do A inverse times A times X equals A inverse times B. And I'm going to do this in MetaCalculator again, okay? But I will actually show you what A inverse is. So let's see, A is a 2 by 2 matrix, and it is 1, 2, 3, 4, and B is a 2 by 1 matrix, and it is 11 and 25. And so let's just look at what A inverse equals. And if you plug it into MetaCalculator, A inverse equals -2, 1, 1.5, or 3/2, if you will, and -0.5, or -1/2. So if I did this by hand, it would have looked instead like -2, 1, 3/2, and -1/2, like that. And you should be able to see how that works. The determinant of A is 4 minus 6, which would be -2, and you do 1 over -2 times A, or times that modified A. So you do -1/2 distributed to the modified A, which would be times 4, and then times -2, and then times -3, and then times 1. And that would give you what we're looking at there. So just so that you understand that, and maybe have a chance to look at that if you want to do it by hand on your own. And then, actually, let me be a little more careful. And then X equals A inverse times B. So X equals A inverse times B, and I will use MetaCalculator to calculate A inverse times B, which gives me a matrix of 3, 4. So that gives me a matrix of 3, 4, which means 3 is my x1 and 4 is my x2. I'll pause again, give you a moment to look at that, see if there are any questions. Okay, there being no questions, I will move on. So now let's do the same thing with a 3-equation system. This is where we actually get into matrices being kind of the more convenient way of solving systems of equations, because once you start getting past 2, the calculations become very long if you're trying to do this by, say, substitution, and even elimination is sometimes very difficult to do. So you start turning to the matrices way of solving these. And one rule that we have that is mathematically true is for every new variable, you need a new equation. So if I have 3 variables to solve for, I need 3 equations. If I have 4 variables, I need 4 equations. And so when we start trying to solve very complicated systems, like, say, weather prediction, weather has tens of thousands of variables to it, then matrices are the only plausible way to do them at all, and sometimes even then it's a really tough calculation. That's why we can calculate, like we can sort of predict the weather out to like 5 or 10 days, but you can't predict the weather for the entire month because the variables are way too complicated. So even this has wide-reaching application, but it is still limited as you start getting up into really high variable numbers. Okay, so let's look at how we would create the equation in the matrix system here. You'd have 1 for the 1x1, and then the minus x2, I'm looking at the first equation here. You have to remember that minus is the same as plus negative, so that would be -1. And then plus x3, or 1x3. And then same thing down for the next row, we have 2, and then plus -1, and then plus 1. And then the next row we have 3 plus 1 plus 3 times, so that's our A, times our x, which is x1, x2, x3. So there's our x matrix, and it equals our constants in one column, so 6, 5, and -20. And that would be our B. And again, we're going to use MetaCalculator, and we're just going to plug all this stuff in, and now we know, I'm going to skip all the details. We know that if we do A inverse times B, we get X. So let me go to MetaCalculator and make it a 3x3 for A and a 3x1 for B, and start plugging stuff in. We've got 1, -1, 1, 2, -1, 1, 3, 1, 3. And then for matrix B, we've got 6, 5, and -20. And if I do A inverse times B, I get -1 and -9.5 and -2.5. And that is my x1, x2, and x3. So I'll let you get a look at that. Pause for a moment, see if there are any questions. Okay, there being no questions, I will move on to our last problem. So in our last problem, we're going to combine a couple of things here. And I'm going to show you some things that will make this a little bit easier, tricks that you might want to use, things of that nature to help you along the way. Okay? So we've defined a matrix Y and a matrix Z, and then we've got this equation right here, 1/2 times the quantity x plus z equals y, and of course we've got an x that we have to figure out, okay? So you could distribute this 1/2. But I want you to notice something. If I do that, that means I'm going to have to do 1/2 times matrix Z, which is going to wind up doing things like giving me -1/2, and it'll be -1, and then 7/2 and 1, which isn't like impossible to deal with or anything like that, but it's somewhat ugly. So what I would rather do is look at this and say, is there an alternative to distributing that negative? And it's just a scalar, so, and we're dealing with an equation. So if I were to multiply by 2 here, I'd get 2 times 1/2 is 1, and then I wouldn't have to deal with distributing that 1/2 at all. And then all I have to do is distribute that 1/2 to the or that 2 to matrix Y. Wow, that's really ugly looking. Let me write it over here. Then I just have to distribute the 2 to matrix Y, which is a whole lot easier, right? So I would have matrix X plus matrix Z, and then if I just go up to Y and distribute a 2 to everything, then I can write the 2 times Y matrix, which will be 8, -10, 4, and -12. Okay? And that will then allow me to do nifty cool things like I need x by itself, so all I have to do is subtract z on both sides. But instead of writing z there, let me write minus what z is, -1, -2, 7, 2, and I can just subtract. Well, subtracting means adding the negative, so let me distribute a negative, that is, change the signs in z for everything, so I'll make this plus, and I'll change all the signs. +1, +2, -7, -2. And then I can just add things together and get a new matrix, and that matrix will be X. Let me do that down here, though, instead. So let's do that down here. So that would mean matrix X would equal, and then 8 plus 1, and I'll do that with each one, is 9, and negative 10 plus 2 is negative 8, and 4 plus negative 7, 4 plus negative 7 is 3, and negative 12 plus negative 2 is negative 14. Oh, and it's negative 3. I apologize for that. And so there's our answer. Matrix X is the matrix 9, negative 8, negative 3, negative 4. Maybe I should make that look like a negative 4 more than it's a, kind of looked like a minus 4 there. All right, well, hopefully that helps you with this section. Thank you so much.